we want to prove that TFL is sound. The proof of soundness is a so-called inductive proof. And so I first want to talk about what inductive proofs are in general before we turn to the proof of TFL's soundness in particular. We have already encountered several inductive definitions in this course. So for example, recall our definition of a TFL sentence. We said that every sentence letter is a sentence, and then we said that if A is a sentence, then not A is a sentence. Furthermore, if A and B are sentences, then A and B is a sentence. If A and B are sentences, then A or B is a sentence. If A and B are sentences, then if A, then B is a sentence. And if A and B are sentences, then A if and only if B is a sentence. And nothing else is a sentence. That was our inductive definition of a TFL sentence. Now, what makes this definition inductive is that it proceeds in two steps. We first define a certain base class. In this case, we say that every sentence letter is a sentence. And that gives us a kind of stock of sentences that we can work with. And then we describe how we can generate new cases from the base class. So for example, when we say if A is a sentence letter and hence is in our base class and therefore a sentence, then not A is a sentence as well. So in the inductive step, we so to speak specify how you may construct new sentences using the stock of sentences that you have in your base class. Now, an inductive proof is a lot like an inductive definition. We first prove that every element in a certain base class of entities has a specific property. And then we prove that when we extend this base class according to certain rules, then the elements of the extended class have the required property as well. So for example, suppose that you want to prove that all natural numbers have a certain property P. An inductive proof of this claim would proceed in two steps. In the base case, you prove that the number 0 has property P, and in the inductive step, you then show that if number k has property P, then number k plus 1 has property P as well. And so that then entails that every natural number has the property P. We have shown that 0 has the property P, and we have shown that if 0 has the property P, then 1 has P as well. And if 1 has P, then 2 has P. And if 2 has P, 3 has P. And so on and so forth. So by going through both the base case and the inductive step, we succeed at showing that every natural number has property P. So let's talk about the inductive step a little more. The inductive step itself has two components. We first assume that number k has property P, and that's our inductive hypothesis. We have not shown that k has the property P, we just assume that for the sake of our proof. And based on this assumption, we then prove that k plus 1 has property P as well. And that completes the inductive step. So the inductive step includes both an assumption, which is the inductive hypothesis, and then a proof that is based on the inductive hypothesis. So, for example, suppose we want to prove the following statement. For every natural number n, 2 raised by 0 plus 2 raised by 1 plus and so on and so forth plus 2 raised by n equals 2 raised by n plus 1 minus 1. We can prove this statement by mathematical induction as follows, by first going through the base case and then going through the inductive step. Now in this particular case, the base case goes like this. We need to show that 2 raised by 0 equals 2 raised by 0 plus 1 minus 1. So if you look into our general statement of what we want to prove above there, you may notice that I simply replaced n by 0. Now we can show that 2 raised by 0 equals 2 raised by 0 plus 1 minus 1 pretty easy as follows. So 2 raised by 0 equals 1, given that for any number a raised by 0 equals 1. And so that means that 2 raised by 0 plus 1 minus 1 equals 2 raised by 1 minus 1, which equals 2 minus 1, which equals 1. And so since both 2 raised by 0 equals 1 and 2 raised by 0 plus 1 minus 1 equals 1, we can conclude that in fact 2 raised by 0 equals 2 raised by 0 plus 1 minus 1. And that completes the base case. Here we have shown that the number 0 has the property that we wanted to prove it has. Now, for the inductive step, we first assume an inductive hypothesis. The inductive hypothesis in this case is that 2 raised by 0 plus 2 raised by 1 plus and so on and so forth plus 2 raised by k equals 2 raised by k plus 1 minus 1. And that's something that we assume. This is our inductive hypothesis. And based on this inductive hypothesis, we now need to show that 2 raised by 0 plus 2 raised by 1 plus and so on and so forth plus 2 raised by k plus 1 equals 2 raised by k plus 2 minus 1. And we can again prove this fairly straightforwardly as follows. First, let's just introduce some brackets. To the left-hand side, you see the statement that 2 raised by 0 plus 2 raised by 1 plus and so on and so forth plus 2 raised by k plus 1 equals the exact same statement, and I just put brackets around 2 raised by 0 and 2 raised by k. So in the first line, the statements to the left of the equal sign and the statement to the right are the same except for the addition of brackets. So that's straightforward, no doubts about that. And now we can use our inductive hypothesis to infer the next step. So our inductive hypothesis tells us that 2 raised by 0 plus 2 raised by 1 plus and so forth plus 2 raised by k equals 2 raised by k plus 1 minus 1. And so what I'm doing in the second line of this proof here, I'm taking the whole thing that was within brackets and replace it by the sentence 2 raised by k plus 1 minus 1. And the reason why I can do that is given by our inductive hypothesis. And then the rest of the proof is simply basic math. I can now infer that 2 raised by k plus 1 minus 1 plus 2 raised by k plus 1 equals 2 times 2 raised by k plus 1 minus 1. And that is identical to 2 raised by k plus 2 minus 1. And that completes our inductive proof. So we have now shown that for every natural number n, 2 raised by 0 plus 2 raised by 1 plus and so on and so forth plus 2 raised by n equals 2 raised by n plus 1 minus 1. In the next part of this lecture, we are going to go on and look at the proof of soundness, which as well is an inductive proof.